When a wave hits an interface between two media at an angle, the wave changes direction. The value of this direction change is determined through Snell's law. We will now discuss the general pattern of these direction changes with change of incident angle. If we start with an incident angle of 0 degrees, the wave will travel through the interface without changing direction. The wave will change speed as determined by the refractive index of the boundary, but it will not change direction. If we discuss a boundary from air to a medium from now on, you can assume that the opposite will be the case for a medium going into air. This scenario means that the wave will always slow down. You can simply reverse all the findings here for a wave speeding up. So, if the angle decreases here, it will increase in a speeding up situation. We increase our angle from 0 degrees so that the wave will refract. At a low angle, the wave will not refract by much. As the angle gets higher and higher, the refraction gets greater and greater, until you reach an angle of incidence where the refracted ray travels along the boundary of the two media. This is called the critical angle, and varies for different media and different media boundaries. Beyond this point, the incident ray will reflect rather than refract, and the angle of reflection will be equal to the angle of incidence. In a vacuum, light travels at its fastest. If we were to create a boundary between a vacuum and another vacuum, the refractive index of this boundary would be 1. So, we can say that the refractive index of the vacuum is 1. Transferring from a gas, such as air, to a solid, such as glass, slows down light considerably. The refractive index of glass is much higher than that of air. When we have an interface with air and glass, we have a situation where you can reflect a wave back into the media, air, as the refractive index of glass is higher than air. In a situation where the refractive index of the second material is lower than that of the incident material, we can generate a value of the incident angle at which the wave will reflect rather than refract. This angle is called the critical angle, and it leads to the study of total internal reflection.